everybody. This is a strange looking problem. In fact, it looks impossible, but you're given a lot of information. Actually, just the fact that you know there's a real number squared that equals this red expression is everything here. Otherwise, this is essentially impossible, I think. One thing you could do to kind of warm up a little bit, there's two is common to each of these. Notice that 120 is the multiple of 4, 140 is the multiple of 4, and 168 is the multiple of 4. So you can actually factor out a 2 here, and you can get 2. Now, as far as I know, this doesn't help anything, but it's just kind of warm up, you know. Now, what's left when you take 4 times 35 square root of 4 is this 2 that you see right here, so you'd have plus the square root of 35, which turns out to be valuable information also, although this isn't doing what the question asked. And then, no, this is 4 times 30, sorry, right here. Okay. And then square root of 4 times 35. And then this one here, I think, is 42. Yes, 42. Now you're saying to yourself, well, what does that have to do with writing it as something squared? Well, you're right. But what happens here is you can pick out some nice factors here. For example, you have 5 times 6 is the radicand here. You have 5 times 7 is the second radicand. And what's this? This is 6 times 7. Now, that gives you a tremendous amount of information moving down to this identity. Yes, this is a very uncommon algebraic identity. And I forgot something right here. This should be times 2. Okay. When you expand that out, you'll get, and there's a 2 in front of all of these. There's actually 9 terms, but they're not all distinct. That explains the presence of this 2. So this identity really comes in super handy right here, because based on what we see up here, you can consider the square root of 5, the square root of 6, and the square root of 7. Okay, and so our number up here, if you take I'll just write it above. If you take a equal root 5, b equal root 6, c equals root 7. Now you see, the nice part about that is that when you square these, you get the 18 that you see right here. See, when you square each of these objects, you get the 18, which is very good news, and the rest of it just falls into place. Okay, again, you got 5 times 6 here, 5 times 7, you have, this is 5 times 6, that's a 30, 5 times 7, and 6 times 7. So you see, everything just falls into place, and then the 2 happens also. Again, I'm not going through every bit of the detail, but it's very easy to check this and see that our answer is the square root of 5 plus the square root of 6 plus the square root of 7. And that's the answer. This is the answer, folks, and it's because all of these numbers just fit this identity perfectly. Remember, these were all, this is 4 times 30, this is 4 times 40, and this is 4 times 42 right here, right? And so the square root of 4 factors out, and that's where this 2 comes in actually right here. Okay, but all that's left is the square roots of 5, the square roots of 6, and the square roots of 7 in various combinations up here. Okay, so this is the answer, and as far as I know, there's no way in the world you're going to get something like this unless you just happen to recognize the form to look for. Okay, because again, it's a tremendous amount of information you're given to be told that this expression is equal to some real number squared. Okay, that's already a ton of information. And it makes you search for maybe an obscure identity. This is not a common identity. It's a trinomial squared identity, but it has to do with elementary symmetric polynomials also. But anyway, that's not really that important as far as this problem goes. But anyway, this is the identity, and this is the only way I know how to solve this problem. So this is the final answer.